Good evening, ladies and gentlemen. Welcome to the first series of INA-IGS Geosynthetic webinar under the theme Slope Stabilization by Geosynthetic in Clay Shale Formation. This event is brought to you by International Geosynthetic Society, Chapter Indonesia, which is also known as INA-IGS. My name is Prabu Manfi, and it's a pleasure to be the master of ceremony of this event. Before we start, please allow me to read the rundown of our event this evening. First, I will be reading the rules of the webinars. Second, there will be an opening remarks by the Vice President of INA-IGS, Mr. Michael Dobi. After that, the event will be guided by Mr. David Saputra as a moderator to start the presentation of Dr. Ingenieur GOUW Tjie-Liong, Master Engineering ChFC. The event will then continue with a question and answer session. After that, the question and answer session will be doing a quiz with a very interesting prize for the winner. So we would like to ask you to stay with us until the end of the event. At the end of the event, we also give you the access to the e-certificate. Ladies and gentlemen, for your own convenience, please put attention to the following rules and notice. You can submit your question for the speaker through the question and answer feature that located at the bottom of the screen, and the question should be in English. You can submit your question before, during, and after the presentation of the speaker. Second, we expect you to stay until the end of the webinar to get the information that you need to regarding the certificate and also the soft copy of the presentation from the speaker. Third, this event is also live streamed on INA-IGS YouTube channel, or you can directly go to the link bit.ly/live INA-IGS Feb 2022. Fourth, if there's any technical difficulties, please contact Mr. Sandi at the number that has been shown on the screen. That's all for the rule and notice. Without any further ado, I would like to invite Mr. Michael Dobi as the Vice President of INA-IGS to give his opening remarks. To Mr. Michael, the time is yours.
Thank you very much for that very nice introduction. And it's my honor tonight to introduce this first webinar of 2022, organized by the Indonesian chapter of IGS, which we called INA-IGS, as you've already heard. Now, sadly today, our president is Dr. Budianto Wijaya, is unfortunately unwell, and he should have been making this introduction, but he's asked me to do it, and I'm very happy to do so, but I would just like to wish that Pak Budi recovers as quickly as possible. And another important part of this opening remark is to thank everybody who's attending today, and also to thank the organizing committee that arranges these webinars, because what I'd like to just summarize to you now is something about what happened last year. So in 2021, we started the idea of these webinar events because of the issues with COVID, because we could not arrange any what we call face-to-face events where we actually meet each other. But luckily, with the advances in all these techniques, we're able to use, in our case, the Zoom platform to present these webinars. And I feel it was very successful. Just to give you a few bits of information about last year, we held 12 webinars, basically one per month, and our speakers came from both Indonesia and overseas, outside Indonesia. And in total, over the entire series, we had approximately 2,800 attendees. And the top single event was actually 438 people attending, which is really very impressive. And also our attendees, in the true international nature of our organization, Attendees were coming from a total of 24 countries. Of course, there's always Indonesia, but many other countries, both nearby and further away. We have people listening in to these events. We covered a wide range of topics during 2021. I'd have to say they were mostly reinforced soil, but certainly not only reinforced soil. And there were other application areas of geosynthetics covered during those events. If you want to find out more about what happened, or you would like to listen again to some of these events, they are available on YouTube. You can contact committee members at INA-IGS who will help you with the link and tell you how to find those particular events. And I can assure you there's a huge amount of really good information tucked away in those various presentations. So now we move into 2022. We did actually take a rest during January, as we're now in February and we're starting these events. And we've decided to arrange a similar program of webinars because just at the moment, we don't have a lot of alternative. Maybe later in the year, we might start to be able to organize face-to-face events and actually meet each other again. But let's just hope that's going to happen. So as we say in English, we keep our fingers crossed that we will be able to do that later in this year. Now, for anybody who's listening in today and they'd be interested in actually becoming a member of IGS, then there is a link available in the chat again, or you can contact committee member of INA-IGS and they will help you with what you have to do. It's very simple to be able to join this society. And I think that really brings me to the end of the comments I'd like to make. I'm now going to hand over to our organizers just to say that tonight our speaker, as you've heard already, is Dr. Tjie-Liong, previously our president. And I'm sure certainly people from Indonesia will be very familiar with Pak GOUW and the work he's done over the years. And what's interesting, especially tonight, is that he's going to tackle a very interesting and potentially difficult geotechnical problem to do with a deposit which we call clay shale. And I think I'm certainly looking forward to hearing about this, as I'm sure many of you will be. So, Pak Prabowo, I'm going to hand back to you and ask you to conduct the rest of our webinar tonight. Thank you very much.
Okay, thank you for your kind remarks, Mr. Michael. Now, ladies and gentlemen, we would like to remind you that you can start to submit your question from now on by using the Q&A feature. We will also want to remind you to stay with us until the end of the event for the quiz session and to get the information regarding the certificates. Now, this webinar will be guided by Mr. David Saputra as moderator. Please welcome Mr. David Saputra. The time is yours.
All right, thank you, Prabhu. Okay, so welcome everyone again to the webinar. We have heard a few times by now that our speaker is Pak GOUW Tjie-Liong, and again, he's not someone who needs an introduction for those who are in Indonesia, of course. But just bear with me for a bit. I'll let you know just a little bit more about him. Of course, he graduated from Unpar, Parahyangan Catholic University, Bandung, in 1984, before going for his graduate study in Thailand, in the Asian Institute of Technology. And just a couple of years ago, he has achieved his doctorate in geotechnical engineering in Parahyangan Catholic University, Bandung, where he is actually currently teaching some postgraduate degrees over there. Yeah. Now, he's been involved in the design and execution of a lot of geotechnical investigations, soil instrumentation, deep foundation excavation for high-rise buildings, load tests, pile integrity testing, and everything. So he has done a lot of work there. And what he has also made a lot of papers, about 93 technical or journal papers in geotechnical engineering, and 23 geotechnical project articles in KON-STR. Now, I don't want to take too much more of your time. I'm sure everyone is eager to hear what Pak GOUW has to say. So I'll hand it to you, Pak GOUW. Let's start this.
Okay, thank you, Pak David, for your kind introduction, and thank you for the committee for inviting me to give the first webinar for INA-IGS for Indonesian chapter of International Geosynthetic Society for the 2022. Now, let me share my screen. All right. Okay. I think the screen is good now. My presentation will be about the slope stabilization by geosynthetic in glacial formation, which was performed in during the 2015 to the 2018, and then it is completed around that year, 2018-2019. This is the content of the presentation. We'll be starting with the introduction, what's the project, what's the clay formation, and the case study for this airport project. Yeah, the project background, the solution adopted, and then the construction process, and some concluding remarks. Okay. This is the Indonesian earthquake zone. Yeah, Indonesian earthquake zone. Move this. First. Okay. The seismic zone of Indonesia, which is, we know that Indonesia is lies on the ring of fire. A lot of earthquake happening in Indonesia. This is one of the project problem. Actually, and then we have many problematic soils in Indonesia. Among others, a subsoil, liquefaction, of course, liquefiable soil. This is the map from Cox, if I'm not mistaken, which I modified a little bit by adding some features. There you see the black area is the soft clay area, the pit area, and then you have also the liquefiable soil in the sandy area. Yeah. We know that Indonesia also have the earthquake which have a lot of liquefaction occurring, including the flow liquefaction in Palu during the 2018. This project is located not very far from that area. We shall see later. Now let us see on the characteristic of the clay formation. Basically, it is a fine-grained sedimentary rock formation, geologically formed by layered clay, sedimented over thousands of years. Then it's hardened due to long-term pressure, maybe millions of years, deep in the ground, and geological event like earthquake has brought the clay shale formation to the near surface. In an unweathered condition, it can have an SPT value as high as 60 blows per feet. As we can see here, let me bring my pen. Okay, this is an unweathered clay formation. It is pretty good. Looks quite firm, quite hard. It's a very good appearance. Then once exposed to outside weather, this clay shell, if we expose to the outside weather like that after we excavate, this one is the excavation Yeah, they excavate. Then we see that not long after, just a few days or few weeks later, it will degrade. It will just degrade and crumble. You see over here, this is from the same area. We took the picture and substantially losing its shear strength. Even if they still look like rock, it is easily falling off and disintegrated by just applying a small force onto it. It can be peeled off layer by layer easily. I have some video to show later how this, you can see how easily we peel off the looks like rock material, but it is easily peel off. That's a weathered clay shale formation. This is a few chunks of clay of soft rocks appear like, looks like intact. Look intact. This one look intact, but it will just with a small force. The rocks, yeah, can be peeled off. This is my hand. I can peel it off. You can see over here, there, yeah, it's crumbled. Yeah, it's crumbled layer by layer. It can be crumbled. Now, if we see the some research carried out by Stark and Duncan in 1991 about the soaked and unsoaked glacial property, we can see that the shear strength of the this glacial formation can have as high as 39 degrees of angle of internal friction, and then we can also have as high as 5,500 psi of C value cohesion, which is equivalent to about 260 kPa. But under the soak condition, after he soaked it for a while, yeah, you can have the cohesion practically drop to zero, yeah, nothing left, and the phi value can become as high, as low as 15 degree, from 39 to just 15 degree. So the physical property changed dramatically. The shear strength changed dramatically upon exposure to the outside weather. This is the research by Gartung in 1986. Gartung have the value of the unweathered glacier. He tested it, then he get it a 41 degree of angle of internal friction, and then this cohesion can be as high as 85 kPa. However, when weathered, its shear strength drop. She is weathering grade 2, grade 3, grade 4, the final stage, and even after prolonged time of exposure, the residual strength just become only 9 degree. That means if we excavate, the slope in the eventually will just flat over 9 degree. That means slope failure will of course take place. And this glacier formation in Indonesia is quite a problematic. In some area, a lot of area has actually, we have this kind of glacial formation. Therefore, slope failure take place quite often, and slope movement also. Yeah. So now we go into the project case study. This project, which I choose to present on this occasion, is that located in Tanah Toraja. Tanah Toraja is located in Sulawesi Island. Formerly, or to many of outside people, overseas people, maybe it is also known as Celebes Island. This Tanah Toraja area is a very special tourist attraction area where you can see the dead body. They just put it in the hole in the cliff area like this. And then we also have this Jesus statue very high over there. Yeah, a lot of culture can be seen there. Yeah, very special one. This is Tanah Toraja, where the project located. And if you have heard about the Palu earthquake, Palu is located somewhere there in the top, the northward here, around there, Palu. Tanah Toraja is this area. This is the picture I took when I went over there. So what is the project? The project is basically a runway. It's an airport project. It is a runway over here to be built over hilly terrain, because there is a lot of mountainous region. And then this airport is meant for better transportation to Tanah Toraja area, because if you go from Makassar, from here to there, it will take about 7 to 9 hours, depending on the condition of the traffic. So the government plan to build this one, and this is under operation already, already successfully built. We shall see later in the end of the presentation. You see here, this is the the coffin, and this is the where they put the corpse like that, that over there. This is one of the coffin as well. Also, quite an interesting area. So the new airport is about 2 kilometers long. The runway is 2 kilometers long. From one end to the other end is 2 kilometers long here, and approximately 210 meters wide. Located in the hilly terrain, massive cut and fill have to be undertaken in order to get the required level of the runway. It is suitable retaining structure. Suitable retaining structure, of course, have to be designed and built to support the high slopes that run along the runway. Formally, the consultant and the projects has been going on before I was involved. A lot of slope failure has been taken place because they don't know about the property of the clay shale material. The previous soil investigation showed that the SPT value is quite high, but upon exposure, upon excavation, this is the former excavation like that, and it's just collapsing. It's just a lot of that collapsing. So high slope has to be built, and if nothing to be taken, no measure taken to stabilize the slope, it's just a lot of failure can happen, and it happened. The maximum embankment height to be built, the maximum embankment height along the runway, this is the runway running that way. This is the 37-meter high slopes. After it was built, we can see the picture later on. It is the highest is 37 meter high, and running from around 15 meter to about 37. These are the two sections that is highest. One is 30 meter, the other one is 37 meter. The initial soil investigation revealed the existence of strong foundation soil. Just 3 to 7 meter depth is already very strong. You see over here, the cone penetration is already CPT cone resistance is already above 150. It's about a 6 meter, 4 meter here also, right? 3 meter, all showing that value is good, right? So it was indicated as soft rock. It was indicated as soft rock with CPT cone resistance greater than 15 MPa and SPT blow cone as high as 60, over 60 blows per feet. So what are the project issues? The first slopes is 15 meter high slope what erected by open cut. Not long after, failure occurred. So the slope failure occurred. It was found that the foundation soil was deteriorated, which was originally to be, the SPT and value is N60. You see over here, this is along a 100 meter stretch to be built, 26 meter height, 26 meter height of slopes, but we can see the soil over here is just degraded, then it's collapsing. It's just like that. Upon raining, upon exposure to outside weather, it's just crumble off and collapsing. So after the failure, some failure take place on what was thought a strong foundation soil. It was later found an existence of glacial, which is easily losing its shear strength upon exposure to the open air. Here you can see, and this is the, let me see. Okay, this is the video. You can see that this is my hand when I go there. Yeah, this look like rock. You see, I can just easily peel it off. Yeah, not a problem. Not a very strong actually. Yeah, looks like very strong, but not very difficult to break it off. That is one of the characteristics of this glacial formation. And we can see over here another one, right? Here, it was reported a few days after it was exposed to outside weather, approximately about 7 to 10 days. Yeah. When I kick it off, it just like that, right? That chunk is the one that I pick off, and then I try to break with my hand just now. You see, it's very easy to break it off, right? So we have many bad experience on construction built over on top on over glacial, yeah, on over glaciers. Many construction difficulty and failure have been found. Yeah. This is one of the picture that I from problematic highway construction over glacial along the previously the Cipularang, West Java, Indonesia. Construction of a glacial require noteworthy care and adequate planning in order to minimize their exposure to weathering agents, in order not to compromise the structure stability. That means we have to construct it very carefully and as fast as possible. In addition to that problem of glacial, we have an earthquake zone. This is based on the sorry, Indonesian standard 2012. Now we have a 2019 one, yeah, the newest one, even higher. This is the PGA for 500 return period, peak ground acceleration. That area, Toraja area located here, is located in the this earthquake zone with a PGA of 0.2 to 0.25 G. Another issue, we only have the cohesive backfill material. We don't have the granular material over there. It's very difficult. Sorry, I have cough. So what are the adopted solution? What is we adopt the solution? We consider different alternative solution, yeah, as required by the Ministry Technical Committee of this airport. One, whether we can do it with natural slope, of course, yeah, as the if we can do it an open cut and backfill just like that without any strengthening of the any reinforcement. Second, we have to consider whether we can use a concrete wall and bore pile, yeah, bore pile as a continuous bore pile, retaining wall probably, and a hybrid reinforced soil slope. This is mechanically stabilized earth, or we also name it as a normally we also call it a geosynthetic reinforced wall. The selection criteria agreed were based on the permeability, on the flexibility, on the construction schedule, and the overall cost, and of course the local manpower involvement. Yeah, as much as possible, we have to employ the local manpower over there. Based on all the above criteria, I will not talk about all these selection. Yeah, the hybrid reinforcement soil structure, or geosynthetic reinforced soil structure combined with anchor gabion units and geogrid was selected as the best suitable solution for this project. So basically, this geosynthetic reinforced soil structure consists of anchor gabion. This is the gabion, anchor gabion with this anchor here about 3 meter length. And then underneath and behind, we put a high strength geogrid. So this is the geogrid, right? This is the geogrid, and the gabion unit is in front. And on top, we put a green facing unit, yeah, composed of steel reinforcement, which they call it as a TerraMesh system. Why it was chosen? Yeah? Because it is much more flexible compared to rigid concrete structure. Then based on the experience in Japan and also in Taiwan, show that this type of structure, as being geosynthetic reinforced structure, perform well under earthquake condition. Remember that this area is also subject to high potential of earthquake, right? And it is easily to construct. It is easy to construct. Local worker can be easily trained to put all that, geosynthetic and also the reinforce can be easily trained, and then therefore we can use, we can employ the local workers over there. Price-wise, it is cheaper than conventional retaining wall. And experience show that it can be applied for high slope. In China, they built it. What I have the information during the one of the conference in India, it was said that it was constructed up to 70 meters high, and in Sikkim, India, it was up to 100-meter high slope. But when I look into the literature, it was reported in the internet. You can have a look on that. In China, it was only saying that up to 50 meter high. So I don't know which one is correct. 50 to 70 meter. Yeah, the information that I got. This is in Sendung Tjie, the same typical, the same construction that I proposed for this project as well. For the Tanah Toraja, it was built up to 50, 70 meter high. But when I designed that project, I don't know about this. Yeah, when I know about this, only when I present this kind of presentation in India in 2018. And this is on Sikkim Airport. It was built in 2013 in India. It is said that in the literature, it is said 74 meter high, 74 meter high. So you see over here, there is also one of the channel here to flow out some water, to throw some water. So they put some kind of what we call conduit over here, right? Below the high retaining wall. The same thing we also have in our project, yeah, to channel out some of the flowing water from underneath the slope. So what we do is that when we try to build this one, of course, first we have to do a proper design calculation, right, which will be explained later. What I suggest is that first we have to manage the water properly by the watering system, if we have water at the bottom of the slope to be built, especially of the top saturated superficial foundation portion. About the first 2 meters is, in some of the area, it is saturated. It's a soft soil practically. Yeah? So we need a soil stripping about 1.5 to 2 meters in order to reach a layer with an undrained shear strength of about greater than 100 kPa, considering this is quite high slope. And replacement of weathered glacial with selected compacted soil. So the weathered glacial, we try to get rid of it also. Provide temporary and permanent drainage system. Then fast excavation and backfilling. Keep exposure time of play as short as possible. So what I suggest the contractor to do, we open it for every maximum 50 meters and complete the installation of the first layer of the backfill material on the same day. Yeah? Try to complete it on the same day. So we do it every maybe 30 to 40 meter wide, and then quickly put the geogrid, put the backfill as fast as possible, especially for the first 1 meter of coverage to minimize the exposure of glacial layer to the environmental agents. So to prevent it to go to experience weathering and losing the shear strength. Right? So first, of course, like I say, managing the water by proper dewatering. Yeah, we cut some pit area and put some pump over there. Yeah, to channelize some water to go in over here, and then we pump it out. Yeah. Excavate over the good clay shale formation and backfill in the limited time as possible. So what we do on the design aspect, yeah. So we based on the data, unfortunately, we don't have time to do the testing as extensive as what have been done by Gartung and Stark, and just now I showed us the chart. So what we do is that we do some, of course, we do also some fractional tests, but not as extensive, So based on this chart, we can see that the design shear strength is recommended is 20 degree. And then with a certain, over here, probably around 20, 20 kPa of the shear strength. So what we adopt based on our testing and also based on this chart, what we adopt is that C prime we adopt as a 20 kPa, and then phi is 17 degree for the first 3 meters of clay, even though I have cleared off the weathering part of it. And then the first 3 meters, I assume lower strength. And this is the lowest strength that I took for that design, for that project. That is, of course, when you ask me based on what, of course, based on this chart and based on my judgment in order to prevent the unwanted situation, right? Unwanted collapse or unwanted performance of the geosynthetic reinforced wall later on. So what we do is this one. This is the first 3 layer at the base, where I assume a lower strength value of the just now C 20 kPa and the phi value of 17 degree. The rest is as per normal, as what we got it, from the testing, and we took the normal value. Only the first layer over here, the first 3 meters, we took lower value, which I name it Tator clay shale number 0. Right? And then Glacial 1, Glacial 2, 3, and 4. And the green one is the compacted backfill material. And this is roughly the formation of the geosynthetic reinforced earth wall. Yeah, geosynthetic reinforced wall. Yeah. So the geosynthetic is lesser in length, and wider at the bottom. Right. So these are the parameters that I took for the evaluation. What we use is we use more Coulomb strength, more Coulomb model. More Coulomb model. This is what I say 2017, and the lower one we got higher. The phi value we got higher, and the glacial at the bottom, at the very bottom, at about this one. The glacial number 4 over here is around probably about 10 meter depth below. We took the full value, almost the whole value. So these are the value that I took for the design, and the design were carried out. The analysis were carried out by limit equilibrium method and also by the finite element method. For the preliminary design, to determine, because it is faster in doing so, to get the length of this, to get the length, every length of the layer, and the strength of the every layer of the geosynthetic that we took, that we use the limit equilibrium software at the first preliminary design stage. Once we got the formation, the design from this limit equilibrium method, then we do a finite element analysis with the Plexus 2D to see how it perform. That's what we do. Then for the earthquake, 500 return period, it was required to take the 500 return period based on the Indonesian standard and the PGA of 0.2, 0.25 G. Since we do a pseudo-static analysis, we don't do the dynamic analysis of the earthquake. What we took as that the horizontal seismic echo coefficient of 50% of the PGA. Based on the reference we got, and also some of the codes that we, it was the project team finally agreed that we took 50% of PGA That's when we assume this one is the PGA of 0.3. Actually, we don't take the really 50%. So what we took is KH equal to 0.15 for the evaluation. Yeah. You see over here, the project is located here. This is Palu, where the 2018 December 2018 earthquake happening that caused a lot of flow liquefaction, and I think it was the largest liquefaction ever recorded, as far as we know. Right. So, what achieved from the design is that safety factor with the limit equilibrium software under static condition is 1.62, and seismic under seismic condition is 1.1, and with Plexus software is about 1.67, and then the seismic condition was 1.12. Not very far different. Not very far different. Is a good match, relatively good match. The minimum safety factor is around 1.5 required. This is what is required by the code, 1.5 and 1.1. So it gives similar safety factors and satisfy the requirement. The limit equilibrium software, of course, we know that it cannot provide the structure, deformation, and settlement. This information, we got it from Plexus. Yeah, but as we go topping up that one, you know that deformation actually, when we built the geosynthetic reinforced earth, reinforced wall, actually the deformation also taken place during the construction. So it will be adjusted. So the shear stress developed in the soil geogrid interface is calculated according to the Coulomb stress criterion. Which means that we reduce, of course, we reduce the shear stress on the soil. This is the geogrid, and then the interface with the geogrid and the soil. We reduce the strength, as we know that we have to reduce it based on this kind of formula. Yeah, this is a Coulomb shear strength formula actually. Yeah, so the tangent phi is the internal angle of friction of the soil. Yeah. That we will take into account for the interface, the interface factor, sorry, the interface angle internal friction will be reduced by R inter, this one here, R inter, reduction factor multiplied by tangent phi of the soil. So the C, the cohesion will also the same, yeah, R reduction factor multiplied by the original soil cohesion. So R inter is less than 0.1. The strength reduction factor can be assumed to be equal to the mu, yeah, over here. Yeah, if we so the pull out, yeah, for the pull out resistance. Yeah. So the interaction factor together from the pull out result provided by the geogrid manufacturer. Yeah, we got, I think, around 0.85. We designed this project. Right. Modeling the gabion facing. Yeah. How we model the gabion facing over here? The gabion facing we model by using a soil cluster. Yeah. So we don't use plate element because plate element is normally, if we use it for vertical wall, probably yes. But if we use plate element, let's say it is a vertical wall, you can use plate element. But on every facing thickness of the face, every what is that, the thickness or every module of the facing, yeah, it is a concrete. Yeah, then you have to put a hinge over here, yeah, so as it can freely rotate. And there is also an option in Plexus, you can put it as free over here, right? If there is you model it as a plate element, but this is an incline. This is an incline wall. Actually, we took some. This is about 45 to 70 maximum height. Maximum slope we designed at that time is around 60, if I'm not mistaken, right? So this is the geogrid. This is the yellow one is the geogrid, and the gray one is the gabion, yeah, gabion facing. So we model it as a soil cluster, and these are the parameters. Take it as drain because water can easily flow out through the gabion, of course. So we took it as drain. Gamma. This is the gamma, the unit weight of this. yeah, it's a bit low with the value that we took, right? This is the stiffness, overall stiffness of the gabion we assume, and the C value is here, and this is actually the phi value. Yeah, we assume as 40 degree. Why we took the C value? Because it's a gabion, it's tied up with reinforced with the wire. Yeah? So we assume there is as a C there. The GeoGrid model were model with the elastic perfectly plastic model, yeah, with a elastoplastic. With the elastoplastic, the strength of the GeoGrid that we use at that project, yeah, at the very bottom one is around 300 kp kilonewton per meter. Yeah. So the EA value will be around 3,900, and the allowable, yeah, plastic axial force when the this GeoGrid or the experience is plastic, the maximum is around 272, taking into account all the damage factor, chemical factor, and insulation factor, and all that sort of things. Yeah. So the maximum allowable strain for this project we assume is 5%. So when we took a 5% maximum allowable strain, we got it around 65% of the ultimate tensile strength. So what we calculate, how we calculate the EA factor is by allowing this stay allowable strength, which is allowable strength. We know that to calculate from the GeoGrid or geosynthetic is that ultimate strength divided by all kind of this reduction factor. This the reduction factor of due to creep. Yeah? This is creep, due to the creep effect. Yeah, and this is the ultimate in the short term one, short term ultimate breaking strength. Then this one is the creep reduction factor. Geosynthetic, when we under stress for a long time, it will creep. Yeah? So we have to take this into account because the airport is designed for 100 years. Yeah? This reduction factor for installation damage. This is the RFID, and the CBD is the chemical biological damage factor. And if we use joint, then there is a joint reduction factor. For this, we don't have a joint. We have for the whole length, we don't cut the and no seams, no joint is used. So for this RFCR, we took as because this after with the 5% strength, the reduction factor will be around 65%. So the RFCR, yeah, the reduction factor for creep, we took it as 1.54. So the long-term design strength is, how do we calculate the long-term design strength is based on the British standard. British standard, the overall reduction factor is 120 years life. PS level and all this is the ultimate tensile strength divide. Then we divide by all the sum of this reduction factor. Yeah, the multiplication of reduction factor. This is the creep factor, and then the damage factor 1.1, insulation damage, and the other one is the other factor. We just took it as 1. So we got the under static condition, we take 180. Under seismic condition, we took 272. Yeah. Then if we go back here, this is the one that when we do the analysis for the earthquake. So we do we increase the this NP value, yeah, the maximum value during the earthquake. Yeah, we take this value, but for static condition, we took this 180. So this is one of the example of the output of this under static condition, the 26-meter height slope. Yeah, predicted displacement will be occurring somewhere around here, about 280 millimeter. This means, of course, the situation is based on the analysis like this is as if we are topping up everything without any leveling up. Yeah, in the reality, it should be, I think it will be lower than this. Yeah? And then under earthquake condition, yeah, with the 0.15 gravitational acceleration, for this 26-meter high slope, the practical maximum movement yeah, over here, the movement outward will be about 53 centimeter. Yeah, but no one knows, yeah, whether this will taken place or not. Yeah, if under a seismic condition. So this is the layout of the construction for the 26-meter high. We have some drainage behind. To stop any groundwater flow, if there is any groundwater flow from the cliff behind. Then this is the original condition, the clay. This is the original ground actually. Then we cut that. We make it. We make the drainage over here. Then the discharge part over there, bring the water out if there is any seepage, to prevent this is from experience any saturation. On the top, we also cover it with grass oil, so that limited soil will be limited water will be seeping through the system. So as not to damage all this, to reduce the strength of the backfill material over here, to prevent it from saturation. Remember that we can only use the clay material, cohesive material to compact. We don't have the granular material. So these are the construction. These are the construction. We excavate. We took out the soft soil, the weathered clay shell, up to the firm one. After we got the fresh, more or less fresh, more or less fresh glacial that we stop. Every excavation is not very wide. You see over there, we stop there. We over here, we excavate. Then we start building up first, covering the first 1 meter at least, covering 1 meter like this. So lay the geogrid, lay the geotextile in front over here, to cover it, to prevent what's that? This one as a separator, and to prevent the later on we put fine grain over here, compact it to prevent it from intrusion to the gabion system, causing loss of particle. Of course, we have to put this geotextile. Non-woven geotextile. So these are the process of the working. This man is laying the stone inside the gabion. Inside the gabion, put it. So this is where we how to lay the geogrid. How to lay the geogrid, the high strength geogrid. Right? Even nighttime, they still do the work, because as I said, to minimize the exposure of the first very bottom layer. So we do it 24 hours a day at that time. So these are the overview of the laying off of the geogrid. Start to the backfilling. Not a very wide area. If you compare, this is the size of the excavator, not very wide, from here to here, so that to guarantee exposure as short as possible, as short as possible. So this is one of the important thing that when we lay this, the track of this, of course, have to walk on to the soil, not directly on the geogrid. If directly on the geogrid, it will just damage the geogrid. So these are the compaction event. Compaction event. Compaction was done layer by layer, every 40 centimeter, roughly, around every 40 centimeter, compact it, and then we test it. Like this. This is the process. Cover the first layer. This is all the completely. Then before moving to the next section and all that. And this is what we do. Again, to prevent the weathering of the base of the glacial. This is the drainage system. Once we go out from the ground level, we start installing this drainage system behind with a geotextile, to prevent the intrusion to the drainage system. All this stone block, the will be placed, and then of course layer by layer, try to as much as possible to compact it in order not to create a weak layer behind, to drain out some water that could seep to from the hill behind. So these are the detail of the discharge system. It's about 25 to 30 centimeter width, and then it's about 80 centimeter. Then we have this right. We have this pipe. Then we channel it out through the outside of the retaining wall, retaining system. And then to prevent, what I worry is that if the pipe is leaked or broken, it will just seep into the ground, and then it will goes into the glacial below. Therefore, I require the project to wrap it around also with the geomembrane. The pipe we wrap it around with geomembrane like this. Then bring it out. Eventually it will be like this. This is after we stage it up. Every stage of this about 1 meter, from the bottom 1, 2, 3, 4, 5. This is already about 5 meter high or 6 meter high, something like that. This is the drainage pipe. This is the detail coming out from the gabion, the drainage pipe. After a certain level, we put not the whole things are under gabion. Some of it, after about 60% of the height, then we put all this the so-called green terra mesh is just by the reinforcement, by the wire mesh, and then so that grass can be easily ground over here. As the facing, because the stress on the top 1/3 is not very high already. So we put like this while we construct, and this is the construction, and this is the construction process when we building up. You can see we have about here is about maybe about 8 to 10 meter high already from the very bottom. This is the compaction process. You see, this is higher and then lower. This is the lower one. It's just compaction like that. Installation is going up step by step like that. So for the very high slope, we have the berm like that. Sloping up, and then it's moving like that. Then we go up like that. Up to the highest one is 37 meter high. So these are the base anchor gabion unit, and then we have this green terra mesh. This is half around 50% of it. We start installing the gabion, the green terra mesh, not by gabion anymore. Only on the bottom part with the gabion. This is the overview of the whole project. You can see this is still constructing, under construction behind the rig. So it's not only the over here. We also install the drainage over there. We also install the drainage. Is something like this is going up. It's building up over here. It's another view. Another view. So this is from the other side. And this is the mulching for the vegetation, for the just the green terra mesh. Just now we show that then we start put some mulching for the vegetation to grow the grass over there. This is the grass started to grow. You can see started to grow in just about probably 3 weeks here, three weeks time, and then the vegetation is growing. You can see over here is already quite a lot, but very unfortunate event happening somewhere when we built about half of the high. It experienced flash flood, flash flood under severe rain. So this is the flooding. The flooding you can see. Let me show the video over here. There's the flooding. It's just like a river. Unfortunately, the contractor haven't have enough time to build the proper drainage behind. So when it's also an unexpected event, the flash flood coming in, yeah, it's just very severe rain. Yeah? The water is flowing through. Actually, some of it flowing through the wall that we have built. Yeah, this is flowing out to the channel. Yeah? I'm very worried. I'm very concerned on that. Yeah, this was happening, if I'm not mistaken, somewhere around July 2016, or yeah, something like that. It's happening like that, if I'm not mistaken. I'm worried. Yeah? I'm very worried. Yeah? But when we see this after the flash flood, it's just washing out the green grass that just have grown. You see, before that, the grass is actually have been quite a lot growing over this area, and it's washed out. You know, washed out, causing some damage, but not like this one. You see some of the spoiling of the soil. Yeah, but it is not very severe damage. It's as a result of good compaction, I think, yeah, I believe, because the contractor doing the job very seriously, and they do the testing and the compaction and in a very good manner, in a very good manner. So the project can go on. Yeah, then we do some minor repair. Yeah, then doing repair. Then condition in 2018 and 2019, you can see that that was happening about 2016, 2017, and then you see over here 2018, yeah, and this is already reaching the highest level over there. Yeah. Then this one, another one, some of the grass already growing. Yeah. Over here, the same. Yeah, is quite thick already. Yeah? The grass is already very thick. There another one, yeah, another view. Yeah. Now this is the when the first plane landed. You see over here, this is the first plane landing, yeah, in the 2020, yeah, August 2020. Let me pause here. You see over here, this is the slope, the retaining wall, yeah, the geosynthetic retaining wall. Then you see there, okay, I pause a bit over here. Yeah, you see this is the highest one, yeah, somewhere around here. Yeah, that's the highest one. That part, yeah? That part is the highest area. That's the when the first plane landing in the August 2018. Yeah? See it once again. See. Now it is already under full operation, but unfortunately I didn't get the newest photo. Yeah, I want to know whether how this appearance already. Yeah, so that is what I have for this presentation. Yeah. Oh, sorry, there is some part that I forgot to present. Let me start it again. Sorry, take a while. Let me share the screen again. All right, where is that share screen? Okay. Okay. So. What is the conclusion? What is the conclusion? This is a sample conclusion remark, concluding remark. Glacial is one of the problematic soil condition. While undetected, can be very dangerous for the stability of the geotechnical construction. This is very often happen because the engineer that handling the situation, the geotechnical engineer handling the situation, doesn't know the performance, the behavior of the glacial. There is if we know it from the very beginning, we can try to avoid the problem. Yeah? The degradation of the shear strength of the glacial can be avoided. The experienced engineer, a proper understanding of the glacial characteristic and behavior is required to handle such difficult ground condition. Of course, in handling all the behavior of the very difficult ground is we need to understand the behavior of the soil. Right? Considering that the strength degrades in just a few days, yeah, construction must be carried out in the fastest time possible. Prolonged exposure of the good glacial layer to outside atmospheric pressure, yeah, to our atmosphere, must be prevented. And reduced shear strength parameter must be adopted in the design process. For this project, we adopt for the first 3 meters, we adopt C on 20 kPa and the 5 value is 17 degree and far less than its maximum unweathered shear strength of 85 kPa and 41 degree. This is what we do on that project. Yeah, the reinforced soil slopes, as long as it is properly designed and carefully executed, can be built on the glacial and using cohesive material as backfill material. Oh yeah, by the way, I have done the similar design on North Sulawesi, one of the island near the Philippines, Siau, the Siau Island. Also for an airport, that the similar system adopted for the 42-meter high. It's a 42-meter high slope. The highest I have ever designed and not built. Of course, I'm only the consultant to do the design 42 meter, but under part of it was under my engineer supervision. Yeah, at least at the very beginning of the project. An engineer foundation soil and well-planned drainage system effectively work to face the weathered glacial foundation. Combination of good understanding of the soil characteristic and its behavior, geotechnical knowledge, design experience, and good construction procedure is required in order to successfully develop a geotechnical structure on a problematic soils. These are the references that I use during the design, also during the write-up of this. And thank you for your kind attention. Any discussion, any any discussion, any question, I hope I can answer some of your question. Thank you. I give it back to Pak David.
All right, thank you for that presentation, Pak. Very, very informative, very interesting. And yeah, just as you were doing your presentation, some questions have already flowed in. We have quite a bit here. How would you like to do this?
Okay, I saw some of the question over here.
Yes, you can.
Okay, maybe I can try to answer over here. From here. First question is from Muhammad Jaki. How much time that glacial need to collapse after weather? That one is from my experience at this project and another project. It can be vary. It can vary from around 2 weeks time to about 3 months, 3 months to 3 months time, roughly like that. By the way, glacial formation also found in along the Cipularang area and also in Hambalang, Hambalang in nearby Jakarta, and quite a lot actually. In Java Island, some of it also we have it, and that what I can answer is around 2 weeks to about 3 months time. It depends also on the slope and on the construction you build. What kind of construction? What is the backfill use when you use the geogrid? This is the question from Sui-Han Wong. Basically, it is from the cohesive material found over there. We, you know that as I mentioned, we do cut and fill for this project. So we cut some of the compactable clay material over there. Then we do the testing, of course, by the proctor test, carried out proctor test of ANSOC, proctor, And then we do the, based on that, we do the select the material for the backfill, So it is a cohesive material, okay. Then the third question is from Pak Michael Dobi. Very interesting presentation concerning the seismic design parameter. If we use a reduced acceleration, then this is normally on an assumption that some displacement occurs should on an earthquake take place. The recommendation in this case is that the soil strength should be appropriate to last displacement. How might this taken into account with the glacial foundation? Yeah, I do agree that as we see that during my presentation, we estimate from the plexus analysis can be around 50 centimeter movement. Yeah. So what are the shear strength that I adopt? The shear strength when we use the dynamic, we use this analysis. Actually, we don't take the peak strength. Yeah, of course, we don't take the peak strength. We take the reduced strength. We take the reduced strength. We take the ultimate strength. You know, where for the design, we don't took the ultimate strength for the design during this design. Yeah, for the compacted clay, we don't do the we don't take the highest one. We took the residual value, the ultimate value. Ideally, what test should be conducted on clay shell formation? This question is from Gani Saputra. The same thing, I think. Yeah, everything is the same test. Yeah, but you have to know that the testing, when we first test it, it is covered by the thick clay soil, thick soil underground there. When we do the SPT test, you can get very high value, 60 plus, above 60 normally. That is why a lot of failure occur after only they excavate and is exposed to the outside weather. So what to be tested? If you want to do the test, probably you just take the chunk of the material, you soak it for 24 hours, then for 48 hours, then you test. Yeah, try to test how much is the strength is reduced. You can do it also by the leave it. Yeah, take the block sample, leave it for a while, and then cut it and put it on a direct shear test. Then you do the test after a few days. Yeah, see how it loses its shear strength. What method could be applied on cut slope that will be exposed? Yeah, of course you have to cover it as fast as possible. You have to cover it as fast as possible, not to expose it to you know, like a situation in Sentul. I was encountering this glacial. I encounter glacial formation back in 1993 when I was called upon at Hambalang, not the Hambalang that's very prominent, but it's a very housing area early in 1993 that is collapsing after they excavate, expose it. They've already built a house, yeah, built housing there. About that time is about 4 months, I believe. Yeah, if I'm not mistaken, about 4 months after they built, then it's collapsed. The slope is collapsed. The slopes collapse because it is exposed to the outside weather. So because they always think that this is good, so they don't cover it. But so the thing that you have to cover, probably you have to shotcrete it, yeah, or you cover it. Nowadays you have all kind of geosynthetic material. Yeah? Maybe you can put GCL, geosynthetic clay liner, yeah, to prevent the rainwater from seeping into the slopes. Yeah? That can be applied. That can be applied. Another question from Tjie-Liong Wong. May I ask about the future maintenance of the structure if there is a clog on the drainage system for the steep slope? This one, frankly speaking, difficult to answer. Yeah. So to prevent the clogging, yeah, but normally because we put behind, yeah, quite a big area to put the drainage, like you see on the picture, I think it won't clog. Yeah? It won't clog if you choose the proper non-woven geotextile, and yeah, then the flush to drain out the water properly. Yeah, I don't think it will be a problem. Yeah, it will be a problem. Never heard about this kind of problem. So was there any UCS value for the soak sample of the shale layer as encountered in the area? Was there any record possible swelling nature? No, we don't do that kind of test over here. We are only concerned about the because we don't do research over here. But in Indonesia, there are many research going on the glacial formation. Yeah, but for this project, we don't do that kind of testing. So from Kin Another question. Thank you very much for the presentation. May I kindly request to know about how to consider the flow effect and the slope stability due to unfortunate seepage and permeability from flooding. We do that by the plexus analysis. Put in the permeability value, put in the groundwater flow, by the groundwater flow, steady state groundwater flow. We do that kind of analysis in by plexus. Of course, we cannot do by the limit equilibrium analysis on that situation. So what was the side slope and shear vertical height of the multi-layered slope restoration measure as adopted? What was the vertical spacing? The vertical spacing of the geogrid layer is varying from 1 to 2 meter high. At the bottom is about 1 meter, every 1 meter. Then reducing to the top, another question now, to prevent how to clog drain due to plant dirt, etc. You in this situation, because the drain is covered, behind is covered by it is inclined and covered with geotextile, and it's a deep layer. I don't believe there will be a plant or dirt coming in. But if the pipe is, we put it under an inclination, in a certain inclination, it's a 4-inch pipe. It won't. I don't think it will have some dirt or plant over there. And you remember that we also cover it with the pipe. We cover it. We also with geomembrane, in order to prevent if any breakage. Then the upper part of the soil material can come into the pipe. To prevent that, we of course we don't want the pipe to break. We cover it with a geomembrane. Was there any geotechnical instrumentation program? Unfortunately, no. Unfortunately, no. I suggest to put some in, and I suggest to monitor. I always suggest the owner to monitor the system, but unfortunately, always budget constraint. There is always budget constraint, and unfortunately, as far as I know, this project is not monitored that far. Was the drainage pipe as provided at the bottommost layer adequate for draining out the entrapped water from existing backslope? Yes, we do the calculation. It should be enough. It should be enough. Because it is not flowing water, it's just to prevent. Actually, the groundwater is deep, deep enough. That should be enough. It's just as a preventive measure. It is not specially designed with the flowing water. There is no flowing water actually was encountered during the soil investigation and during the construction of the slopes. Except the surface water due to the flash flood, as we have seen just now. What was the side slope and the shear vertical height of the multi-layer slope restoration? That one, the same thing, I think,
That was the same
before. Do you think if the backfill on toll road use glacial in combination with geotextile? What you mean backfill glacial material? Degraded glacial material, then we use it as a backfill material in combination with geotextile. I think that one you have to check whether the glacial after it's degraded, and or you have to check, you compact it, whether then you soak it, whether it will undergo swelling. If it has a very high monolinette content, maybe it will swell. And then if it is swell, if you use it on the toll road for that, I don't recommend it. Toll road is a very high speed road. I don't recommend it. You have to test it first whether that can causing some heaving, and if there is heaving, the toll road will become wavy. It will be a problem. Except if you can maybe if you can protect it from water seeping into the compacted glacial material that has been degraded, if it is compactable, yeah, you got to check that first before you can try to apply it, to use it as a backfill material. Then the last question, interesting presentation. I want to ask, can the excavated glacial material be used as backfill? This is the same thing. Yeah, you got to test it. Yeah, you have to test it. Maybe if for not for significant construction, not a high risk construction, probably we can use it. Yeah, probably we can use it. But I never use that. Never have that kind of experience. And what was the global stability analysis done considering the strength and the existing glacial base slope? Yes, you can see that in my data just now in the micro section. Yeah? That is, of course, it is taken into account. The internal stability is basically analyzed by using limit equilibrium analysis. Okay, that's all from what I can see
yes,
over here.
You have answered quite a lot of questions there, Pak Go. Thank you. Thank you for that. It is. It was quite interesting to see the different questions there. One of the ones that I found very interesting is the one where people are asking about the possibility of the drainage being clogged and all that. Like you said, you know, it's once it's properly enclosed with the geotextile. You know, of course, you pay attention to it when you're doing the installation. You wouldn't expect any cloggings there, especially not from plants, yeah, because it's so deep inside. Without sunlight, it won't grow anyways. So yeah. So I think, yeah. Sorry, did you have anything else to add?
That's all, I think.
Okay, yeah, I think
the message that from this is the most important thing is we have to understand the soil we encounter. Yeah. So as a geotechnical engineer, when we read a report, you must a geotechnical report, you must carefully read it, and then as much as possible, we have to see the core sample if possible and go to the site, see the core samples. Because if the people doing the soil investigation doesn't understand the situation, they may not report it is as a glacial. Most often they report it as a clay stone. When you see the clay stone in the report and like that, or mudstone, probably you have to request for the sample, yeah? Or request for the core sample and have a look on it, see whether it is a glacial or not. The easiest way to identify a glacial is that if the core, the fresh core sample from the site, you get it, then you just expose it to weather. Yeah, then you can see maybe 1 week later you can see whether it will degrade, the shear strength degrade or not. There is normally in a glacial formation you can see a lot of seams, yeah? Like Indonesia kue lapis. You can see that kind of layering. After a while you can see that kind of layering, and that is a glacial formation. Then you can check, yeah, by just like what I did, peeling it off, yeah, before, just after taking out, then after maybe 1 week later, 3 days later, you try to have a look on that. Then you can identify whether it is a glacial or not. You just rely on the report, on the SPTN value, on the all that sort of things. You may not know it, yeah, whether it is a glacial or not. Thank you.
All right, you just gave a very good summary, but that was the biggest takeaway from me as well, from your presentation, that we have to be a lot more careful. Looking at the page, looking at the numbers, it can be very deceiving. We think, oh, everything is good, yeah, and then it turns out if it really is glacial, and it will start deteriorating. I mean, it starts getting weaker and weaker after it gets weathered, and it can be very dangerous. So thank you for your time, Pak. And I think it's time for us to give the time back to Prabu.
All right.
Okay.
Thank you all.
Thank you to Dr. Go for the presentation. And also thank you to Mr. David as the moderator for guiding this session. Okay, now we are heading to the quiz session that will be guided by Miss Riva. Please welcome Miss Riva. The time is yours.
Okay, thank you, Prabu. Ladies and gentlemen, good evening. My name is Riva, and I will be guiding you in this very short game we have prepared. And the questions are all prepared by our speaker, Dr. GOUW. The total prize will be 250,000 rupiah, and the first winner of the quiz will get 150,000. Then the second winner will get 100,000. To give you a disclaimer before we play, everyone can join this quiz, but for technical reasons, only those who live inside Indonesia are eligible to get the prize. You can now directly go to your browser on your phone or your PC and type menti.com, 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 and you have to type the code number shown on your screen or also there in the chat box. The code is 88633276. Once again, please go to menti.com from your phone or your PC and then put the code 88633276. Then fill in your name and make sure that it is the name that you submit in the registration for this webinar. So later, if you win the committee, we'll easily contact you for the prize. Remember, the prize is very interesting. We have prepared 250,000 rupiah for the total. For only two winners tonight, and you will not want to miss this chance. For those who live inside Indonesia, especially because you are eligible to get the prize. So go to menti.com, put the code 88633276 and fill in your name. We will be waiting for more attendees to join, but let's see. Let me share my screen first. Hang on. Okay, I think many have joined us. I will still be waiting for another minute. Please go to menti.com and then type in the code 88633276. So how to play this game? There will be 3 questions, all prepared by our speaker, Dr. GOUW. And you have to choose the correct answer, but not only correct, you have to be fast to get more bonus point. Okay, 55 people and counting. I will still be waiting. Go to menti.com. You can play it on your phone, on your PC, and use the code 88633276. Don't forget to put your name. If you forget the name that you registered on the webinar, you can see it on your Zoom display name right now. Okay, I'm going to count down 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Let's play. Okay. Answer fast to get more points. For the first question, according to the study of Gartung, what is the internal friction angle of unweathered clay shale? A, is it up to 26 degrees? Or B, up to 35 degrees? C, up to 41 degrees? Or D, up to 45 degrees? According to the study of Gartung, what is the internal friction angle of unweathered clay shale? You have 20 seconds from now. Is it A, B, C, or D? Up to 26 degrees, 35 degrees, 41 degrees, or 45 degrees? Okay. 5, 4, 3, 2, 1. Time's up. Let's see what is the correct answer. The correct answer is C, up to 41 degrees. Let's see who lead the first leaderboard, but not win yet. We still have 2 more questions. For the first question, who lead the board is Delphian with 978 points. We still have other 2 questions, so brace yourself. Second question. Answer fast to get more points. points. Clay shale, which has not been exposed to air, has a high cohesion, about 90 to 260 kilopascal. What cohesion remains after complete weathering? The options are A, 0%, B, 25%, C, 40%, or D, 50%. Clay shale, which has not been exposed to air, has a high cohesion, about 90 to 260 kilopascal. What cohesion remains after complete weathering? Is it A, B, C, or D? You have 10 seconds left. Is it 0, 25%, 40%, or 50%? 3, 2, 1, time's up. Let's see the correct answer for the second question is A, 0%. Okay. Let's see for the second question. Yep, the leaderboard is changing. Let's see for the last question. Who will win tonight? There will be 2 winners. Answer fast to get more points. From these reinforced soil wall projects, which height is correct? Is it A, Tanah Toraja with 37 meters, or B, Shenong Chia at 74 meters, or C, Sikkim at 50 meters? From these reinforced soil wall projects, which height is correct? Is it A, B, or C? Is it Tanah Toraja with 37 meters? Is it Shenong Chia with 74 meters? Or is it Sikkim with 50 meters? You have 50 seconds left. The last question. This is going to be the decision of the night. 3, 2, 1. Time's up. Let's see. The correct answer for the last question is A, Tanah Toraja. There are 51 people who answer correctly. Let's see who will win tonight. There will be only 2 winners. 4. Okay, we have our winners. Congratulations to Iman Alfikri with 2,919 points. And the second winner is Meta Devi Hartadi with 2,886 points. You can screenshot for the 2 winners, you can screenshot the screen and then send to the committee, or later committee will also approach you. Okay, everyone, thank you for playing tonight. I hope you guys have a good rest after this. I'll give it back to Prabu. Thank you.
Okay, thank you, Ms. Rifa, for guiding the quiz session, and congratulations to all the winners. Now, we would like to invite you to join the next Geosynthetic webinar series on 30 March 2022 with the theme Railway Ballast Stabilization and Mitigation of Ballast Degradation using GeoGrid. The speaker for the next webinar will be Mr. Errol Tutumor, PhD. You can register via the link bit.ly/INA-IGS Mar 2022. We'd like to inform you that you can access the e-certificate and also the soft copy of the presentation from the speaker at the link bit.ly/info-INA-IGS Feb 2022. Well, ladies and gentlemen, now we have to come to the end of this webinar. It's been a pleasure being with all of you today, and thank you for the participation. Hope we could see you in the next webinar, and I wish you all a very good evening. Always remember to stay safe and stay healthy. Goodbye and see you in the next webinar.